So really quick, I went ahead and I posted all of the test date over there on the board. So you got unit 5A. The first test is going to be on October 20th. So today is the 11th. Okay, so that's coming up. The next one is November 6th, then November 17th, then December 7th. Your EOC for this course is on December either 10th or 11th. I don't know when. I know that's either one of those dates. Okay. Then you'll have your final exam after that. You need to do well on the EOC. Remember, the EOC is both quarter 1 and quarter 2. It's not just quarter 2. So don't throw away your stuff from quarter 1 because you're going to need it. Okay. In this unit, we will have 3 mastery checks. Okay. So we'll have one on Friday. And then we'll have one on, we're going to try to do it Tuesday, Wednesday, and then we'll test on Friday. Okay. So that's how that's going to go. Okay. On Friday, the mastery check basically asks you for all the key features of exponential functions. So if you weren't here yesterday, we're going over them really quick, and then we can kind of go from there. So on this first one, if you fill in the table, okay, and you can pick any x values. You can pick any x values to plug in. I just like these 3 numbers because they're easy. When I plug in 0, 1, and 2, what do I get? Yes, the stunned silence. If I plug in 0, I would have gotten negative 1.75, right? If I plugged in 1, what would I get? Okay. If I plugged in 2, what would I get? Fantastic. And I'm going to graph those really quick. So 0, comma, negative 1.75. Somebody asked me yesterday, how do you graph a decimal? You kind of just do a rough sketch. Okay. 1, negative 1, 2, 2. Okay. And so this is what it's going to look like. Are there any y-intercepts? Y-intercept? Fantastic. Are there any x-intercepts? Okay, how do we figure that out? This one's a little tricky to like just visually see. So I would suggest maybe going into Desmos and typing that one in. So that way you can see exactly where it crosses the x-axis. So when you go into Desmos, I got too many tabs open. All right then. 1/4 times 4 raised to the x. Is it minus 2? Yeah. Okay. So where does it cross the x-axis? 1.5 comma 0, right? Okay. So the x-intercept is at 1.5 comma 0. Again, how I did that was I plugged it into Desmos. Okay. On your mastery check, it's an easy enough one that you can see where it crosses the x-axis. Okay. For domain, what is the domain of all exponential functions? Negative infinity to positive infinity. What is our asymptote in this function? Y equals negative 2. Remember, whatever is that number that's added on the outside, not in the exponent, but on the outside, that's your asymptote. Okay. What's our range then? Negative 2 to positive infinity. Okay. Normally your range is going to be either negative infinity or positive infinity. So whatever your horizontal asymptote is. That's normally what this is going to be. Transformation is a little tricky. So this horizontal asymptote at negative 2 means that we shifted down 2. And this 1/4 out front means we shrunk or shrink by 1/4. Okay. If it's a number that's greater than 1 out front, then that's going to be a stretch. Okay. I'm going to give you 30 seconds to do number 6.
And what is the shrink?
Sorry. Okay. The domain is negative infinity to positive infinity. Your your asymptote is y equals negative 3. So that means your range is -3 to positive infinity. Your y-intercept, I got 0, 0. What'd you get? 0, 0. Okay. Transformations, I got down 3 and stretch of 3. Okay. What do I get for x-intercepts? There's not one? Okay, let's plot it and make sure, okay? Does it cross the x-axis? Yeah, we're at 0, 0. It's okay for your y-intercept to be the same as your x-intercept. That's okay. Okay. And then when I plug in 2, what did I get? Anybody know? Say it again. One -2.5. It should be decaying, so it should be going this way. Yeah, so it should be a negative, right? Maybe. Yeah. So there should be -2.81. Cool. Okay. Questions on that? Do we need one more? All right, try 7. This is what I got. Okay. I graphed it so I could figure out what the y-intercept is and the x-intercept is. Okay, so that made that easier. But I could have plugged in 0 for x, and that would have given me my y-intercept for x. So if I wanted to find the y-intercept by hand, I would plug in 0 for x and then just simplify it. Okay. Now, if I wanted to find my x-intercept, I would have to set this equal to 0 and then solve, but you don't have to do that. So domain is going to be -infinity to positive infinity. Range, this is new, is going to be from -infinity to 1. The reason why is because this negative filling out front is going to create a reflection across the x-axis. This is the new one. Reflection across the x-axis. Do we see how it's facing like downwards? Okay. That's where that's coming from. So we moved up 1, we shrunk 1 by 1/2, and we reflected across the x-axis. Okay, just looking at the last one, we're just going to do the transformation really quick. What is this -4 going to do out in the back? Oh, talk to me, please, so we can move on. Okay, so down 4. Okay, what about the 4 out front? Stretch of 4. This is one that we haven't seen in a while. This +3 means that we're going to move left 3. Okay, I know it's positive, but it's almost like, you know, the opposite of what you would think it would be. So it's going to be left 3. Okay, again, we could see that from the graph as well. We're going to press play to see how the kelp and the sea urchin populations change over time. Make a prediction. What do you think will happen in the future to each population? So what do you think is going to happen to the kelp? The kelp's the green stuff, and the sea urchins are the purple things. What do you think is going to happen in the future to each population? Go ahead and type that. Okay. So some of y'all were saying that the decrease in kelp population, increase in sea urchins. Great, awesome, fabulous. Okay. All right, on slide number 2, we're going to press play to see the urchin population after T months on the graph. Describe the graph. All right, so describe the graph. Max. All right, so how would you describe this? How would you describe this? It's increasing. Okay. Now sketch what you think the graph's going to look like in the future. So you're going to just continue that graph, right? Make a prediction. How many sea urchins do you think there will be after 35 months? So right now we're almost at like 10, and there's like 15-ish sea urchins. Make a prediction. Some of y'all are saying like 75 to like 100 or maybe 50. Okay, cool. All right. On slide 4, It says, here are the sketches that these two people made. Describe the key features of each sketch. Use the vocabulary below that helps you with your description. So you're telling me positive, negative, domain, linear, minimum, range, increasing, exponential. Take a moment, describe each one of these sketches. Okay. Okay. So somebody else said that, or whatever her name is exponential and it's increasing. Good. Some say it's a curve, some say it's positive. What makes it positive and negative? Do we know? Sort of. Positive is above the x-axis and negative is below the x-axis. Okay. There's a difference between increasing and being positive. Positive is, again, above the x-axis. You can be increasing and below the x-axis. At some point, yes, you will cross the x-axis and then you will become positive, but you can be negative and increasing. Does that make sense? Okay, a little confusing, I know. Okay. On Omari's, what kind of function is that guy? Linear. Okay, it's still increasing. Okay, is there a minimum value or a maximum value on this one? Well, there's probably a minimum value because we have an initial, but there's not a min or max. Okay. With domain, wouldn't they be the same? It will cover the same amount of time. But what about range? This range would probably escalate higher at a faster rate, right? Okay. All right, looking at number 5. Press reveal to see the number of sea urchins after 35 months. Reveal. How close were you? So that's 112. Somebody else had like 100. I think somebody did get 112 because they probably skipped ahead. Okay. During which months does a linear function model the population well? Which one does it not model it well? Okay, so we're on slide 6. Take a moment. Okay, so somebody else said 0 to 10, 0 to 13. So probably about 0 to like 15-ish would probably be okay. And then it starts creating like a big difference, right? Okay. Here's an exponential function that better models this sea urchin. What is the value of u of 48? What is this really asking you to do? What is it asking you to do with that 48? What is it asking you to do with that 48? Okay, plug it in, right? Okay, so we would say 4 times 1.1. We're going to raise it to the 48th power. And how many sea urchins do we have? 388, right? Ta-da! Now, can you have half a sea urchin? No, you probably would run around, right? But for this purpose, we're just going to keep it the exact number. What does this solution tell you about this situation? So let's look in context. When we want to look in context, we're going to look at the sides. So you see how it says time in months right here? And then on the side, it says number of sea urchins. So when we hit 48 months, how many sea urchins were there? 388. So when we hit 48 months, actually hear you typing, we would have 388 sea urchins. Good. So checking your work, I'm gonna use Vanessa as my example. She said that this U of t equals 120. That means that there's 120 total sea urchins after t months. Okay. The total number of sea urchins after 120 months, that's what this represents. And the total number of sea urchins after 5 months ago. Okay. The 5 months ago, that's negative time. Technically, you really can't talk about previously, which in time, but some instances you can. It's a little weird. Okay. All right, let's move on to the next slide. Yeah. All right, this gives an approximate number of sea urchins after T months. According to the model, how many sea urchins will there be after 120 months? So think about where are you plugging this in and see how many there are. Take a second, try it. Okay, so most of you probably did this. And you got 370,836 sea urchins. 370,836. Ta-da! Okay. All right. Number 10. The sea urchin population can't grow exponentially forever. What factors might affect how the sea urchin population changes over time? Okay. So what things could impact this? Some people say diseases, predators, not enough food. Starfish are starfish like mean to sea urchins? Are starfish like predators to sea urchins? Are they really? Wild. I didn't know that. Okay. We should look up like what are predators to sea urchins? I don't know. Overpopulation. Good point, Michael. Okay. So all of these things could impact it, right? Now, number 11. Here are some graphs that show how the sea urchin population could grow. Select a graph and write a story about how the sea urchin population changed over time. Okay, so you can pick any graph, but you got to tell me like what happened. Okay, take a second, try that one. We're almost done. Okay, so I'm gonna pick Alejandro. He said this graph, and he said the sea urchins will decrease, but the population could go up. And then I don't know what you were gonna finish saying. So it would increase, it would decrease because of something, and then maybe like kind of hold it steady, right? Okay, good. All right, let's go ahead and go to slide 12. Select one of the questions to answer. What is something you learned about using functions to model how populations grow? Or what is a question that you have about sea urchin population? Pick one of the questions to answer. All right, and then go ahead and go to slide 13 and go ahead and answer this. So this is telling me whether or not you actually understood what we talked about today. So go ahead and take a moment, try this. So on slide 13, don't change anything yet, okay? But what words can we describe with this? Yep, good. Okay, positive, increasing, and linear. How do we know that it's positive? Above the x-axis. How do we know it's increasing? It's going up from left to right. Remember, you read left to right, so you have to look from left to right. Okay, how do we know it's linear and not exponential? Ooh. Okay, look at the equation really quick. Okay, look at the equation. Is there an x in the exponent, or is there a variable in the exponent? Is there a variable in the exponent? Is there a t that's up in the exponent? Yes. So is that linear or is that exponential? It's exponential. So this one should be exponential. Okay, yeah. So here it is again. Linear functions look like this. They do y equals mx plus b, right? And they're a straight line. Now, exponential has that x in the exponent, okay? Sometimes exponentials can be like really drawn out, and we're only looking at this part of it. Does that make sense? And sometimes that kind of looks like a straight line because it's taken 5 ever million years to finally like curve up. Okay, but you have to pay attention to the equation as well. Okay, now what does a of 2 equal 4,410 tell you about the situation? What does that tell us? Okay, so 2 months. How many sea urchins, right? 4,410 urchins. So in 2 months, they'll have 4,410 urchins. You have to be able to interpret this in context. Okay, this right here is from like unit 1. Okay, you got to be able to do that. Okay, Gucci. Okay, so on here are 2 examples of a linear and exponential relationship. Let's compare the 2 types. In order to fill this in, again, you could either go to Desmos, but let's say like on your mastery check, you don't have your Desmos, right? If I take 0 and I plug it in here, that's going to be 30 plus 20 times 0. What's 20 times 0? 0. 0 plus 30, 30. I'm going to do the same thing for when it's 1. So all I'm going to do is plug in 1 into that. Well, what's 20 times 1? 20. 20 plus 30 is 50. Okay, going to do the same thing when it's 2. That's going to give me 70. I'm going to do the same thing when it's 3. That's going to give me 90. Everybody see how I filled that in and I didn't have to plug it into Desmos?
You're joking.
So for that X, I'm going to substitute in all of these numbers. Okay. On the next one, I'm going to do the exact same thing. Okay, so I'm going to plug in 0 into this equation. So I'm going to say 5 times 2 raised to the 0 power. That's going to give me 5. If I plug in 1, that's going to give me 10. If I plug in 2, that's going to give me 20. Okay, at first in this table, I need you to look. At first in this table, what was our initial amount? 5. Then each month, what's happening each time? What are we multiplying by? 2. Each month we're multiplying by 2. So watch this. Y'all gonna miss it. The initial is 5. That's the number that's out front. The number that's raised to the X is the ratio or what you're multiplying by each month. Okay? All right, so you could graph these. I'm gonna do it like a real quick sketch. Why are y'all so giggly? Like, that's weird. Stop it. Making it worse. It's the fact that I'm recording and you can hear all of your giggles in the background, so that's fun. 20. Okay, so this is what these 2 graphs are going to look like. Where's my initial amount? Where's our initial amount? On that y-axis, right? Our initial amount is the y-intercept. Okay, where do you see the growth factor or the rate of change? The rate of change is my slope for linear, also known as rate of change. Okay, the growth factor is this 2. After 10 months, which one's going to produce more? Well, let's say that we don't have that graph. We can use our equation for both of these, and we can plug in 10 for both. Let's do that. So what's 20 times 10? 200. 200 plus 30 is 230. Over here, if we plug in 10 for that x, what's 2 raised to the 10th power? Something. And thanks, guys. Appreciate it. Okay, so if we come in here and we say 5 times 2 raised to the 10th power, what is that going to give me? 5,120. So 5,120. So, unless you have the graph and you see it on the graph, probably not. Okay, which one has more? Exponential. Okay, the farther out you go in the number of months, the more that exponential is going to have more. Notice how the linear function started off with more at the beginning, but exponential picked up faster. It's kind of like a roller coaster. So like, if you have ever ridden the Scream Machine, at like Six Flags. I hate that roller coaster. It's so like rickety. It's like so trash. Okay, so the screen machine goes like this, right? It's like very like, I don't want to say smooth, but it's like consistent, right? And then Goliath is literally like you get on it and it's like starts off slow and goes up and then comes back down. Yeah. I think of Goliath as being like exponential and the screen machine being more linear. I mean, I know there's a little bit of a curve to it, but it's more consistent. Yeah.
The screen machine
Oh.
always keeps going up and down.
The screen machine's too rickety. When you get old, it hurts. Yeah.
First,
Okay. Go ahead and flip over the page. Go ahead and flip over the page. I need you to be able to tell the difference between linear, exponential, or quadratic. All right, shh. Let's lock in. Ready? Okay, how do we tell the difference between linear and exponential?
linear is a straight line.
Linear is a straight, okay, but from a table. What do you mean fill it out? So the first difference and all that. Okay, first difference on this one is 10, and then this one's 30. Okay, so is that the same first difference? No. Does it have, we can't really tell if it has the same second difference, right? So this is going to be something else. On this next one, we have 10. Oh, I'm sorry. Go back. Pause. On here, can we multiply by something to get the next number?
Yeah.
Yeah, what is it? 3. I can multiply by 3 each time. If I multiply by 3, that's considered exponential. If there's a ratio that's being multiplied by, that's exponential. Can you take a moment? Can you decide these two? On the next one, the first difference between these, 100. Good. Is there a number that we can multiply by each time to get the next one? 10. Okay, so we can multiply by 10. Is that linear or exponential? Exponential. What about the next one? Why do we know it's linear? Okay, it has the same first difference the entire time. Okay. We're gonna skip that one. Okay, how do we know if this statement is true? What is this statement saying? This is saying when we plug in 6 for f, that's this first function, it's less than the g function when we plug in 6. So let's check it. If we plug in 6 on this one, and then we plug in 6 on this one, which one's bigger? So we're going to go into our graphing calculator, and we're going to say 2 times 3 raised to the 6. And then we're going to say 3 times 2 raised to the 6. So this is 1458. This is 192. Oh, sorry. So coming back over here, was this function less than this function? No. False. Okay, and all you would write is this down here.